My name is Derek Emma. Okay, I'm going to be talking about post-quantum Zcash. If I was focused on the right window, there we go. So yes, the trans community is under attack in the US and other countries, and yeah, this talk is for that. So what's a quantum computer? Well, if you ask Google, given how far Google search has gone downhill, it will give you the silly answer that it's true of all computers. All computers depend on quantum mechanics, if they're using silicon chips anyway. But okay, let's try and get a better answer to this question. So there's this thing called the invariance thesis, which is it's about sort of the computational power of computers and how efficient computers can be. So you might know about the Church-Turing thesis, which says that sort of models of computation like the lambda calculus or post systems or Turing machines can all compute the same things. So a strengthening of that is that not only can they compute the same things, but they take fundamentally sort of the same complexity to do it in both time and space, and that can be made more precise. But the sort of the interest in quantum computers is that sort of idea may be wrong. There may be types of computer that can be fundamentally more efficient at some problems. And in particular, we think that there might be an algorithm that can compute discrete logs, say. And so if that were true, if it could compute that in sort of exponential time, then we would have evidence that this invariance thesis was false, which is it's kind of important because that means we're in a whole different set of complexity assumptions than we thought we were. Okay, and despite all that, the hype around quantum computing, this is actually a falsifiable hypothesis, and so it's an interesting scientific question, despite the hype. Okay, so what kinds of problems can we solve potentially with quantum computers? Well, like the slide says, Daniel Simon was actually trying to prove the opposite, that quantum computers could not obtain an exponential speedup. And he couldn't prove that. And so he found even relatively simple circuits could be a counterexample to this. So here we have a function f, and this UF here is computing the function in a quantum circuit. And then there are these other things around here, which I'll explain later. And these are measurements. So we're starting with some state, computing the function on it, doing this other thing, and measuring the result. And it turns out that's enough to demonstrate that the original hypothesis that quantum computers were kind of equivalent to conventional computers, classical computers, was wrong. And this was a huge breakthrough. So he submitted a paper to this theory conference, imposing on theory of computing, and it got rejected because anything that's fundamentally new will get rejected, as we know. Okay, so fortunately, Simon had a really good thesis supervisor, Peter Shaw, and he noticed the similarity of the kind of artificial-looking problem that Simon had come up with to demonstrate the speedup was very similar to some existing number theory problems. And in particular, So this hidden subgroup problem, so particular instances of it could be used to solve factoring in discrete log. So Shaw generalized it, and sort of happily ever after, because both of those papers were published in a competing journal. So that be a lesson to reviewers who are not capable of seeing fundamental advances. Okay, so although Shaw's algorithms are more directly useful for cryptographic problems, we're going to talk about Simon's algorithm, because I think that's the intuition you need for understanding how quantum computers can get speedups at all. All right, so this is the problem. Says we have a secret value S, which is a bit string. So you have so n bits in the case that Simon originally considered, and we have a function that maps from those n bits to some other space, and that has the property that well, I'll describe it informally. So the function has sort of copies of itself shifted by some secret bit string S, and the shift operation is just exclusive for. Okay, so this looks like a fairly artificial problem, but if you place 0,s here with some subgroup, so G is a group, and you place this with a subgroup, then that is exactly the hidden subgroup problem. And so we're trying to find S. So if we find a collision on F, then that immediately gives us S. Actually, X and Y are non-equal. So we know that we can solve this classically in square root of the size of the group. And so in general, for a sufficiently well-behaved group, it can be proven that if you don't know anything else about F, then that's the best you can do, basically. Okay. So we need to know a little bit of quantum theory to understand what's going on here. And so like you can model so classical states using probability, you can model quantum states using something called amplitude, sometimes called probability amplitude, but I think that's a bad name. And so the space that you're trying to, the space of possibilities. So in this case, so possible values of your bit string. Each of those has an amplitude, which is a complex vector, and I'm probably going into too much detail here, but the idea is that you have a particular kind of transformation on these states, and you can measure states, but the probabilities end up being a little bit weird. They're not how you would expect. So when you measure the probability, you get the square of the amplitude, not the amplitude itself. And that really is the key to why quantum theory is weird. And so measuring these states destroys them, which is kind of inconvenient. But what a quantum computer is fundamentally, it's something that operates on these quantum states in ways that depend on this sort of difference from classical probability. Okay. Yeah, I'll skip this. We don't really need to accept that Yeah, so you'll have heard about qubits. A qubit is basically just it's part of the state of a quantum computer that can be in a superposition. Right. So we need some kind of classical mathematics. There's nothing fundamentally sort of dependent on quantum computers about this. So there's this thing called the Walsh-Hadamard transform, which is like a Fourier transform. So it's going between the computational basis and a frequency basis, and it's doing that for this group of bit strings, basically, under exclusive OR. So exactly the group that Simon's algorithm is operating on. And if we were going to, how this works is sort of apply your function f to every possible bit string. So these are the sort of resulting outputs. And then you apply this thing, which is like a fast Fourier transform, and you get some output that encodes information about the function. And in particular, it's interesting information to find things like this hidden shift that we're trying to find in this problem. But we can't compute the whole thing because it would take 2 to the n bits times n complexity. But you don't need to. So what the quantum algorithm does is very efficiently, it will compute a superposition over sort of all of these output states. Okay, and then the overall algorithm is you set up a superposition of n qubits, just uniform here. And these are zeros. What I didn't say before is that you can only do reversible computations in a quantum circuit. And so get out the result of applying the function to that, and then you apply the Walsh-Hadamard transform and you measure it. And so what happens here, and I'm not going to explain in all of the maths, but you get a kind of interference pattern between the outputs. And it turns out that sort of the outputs that can actually be measured here are all of a particular form that gives you one bit about the secret value S. And then you just solve this system of equations. So if you've got n bits of information, then you can solve them to find S. So that's basically all it is. And so I think there's a lot of kind of mystique and sort of woo about how people explain quantum physics and quantum computation, and it's really not that mysterious at all. A lot of it is to do with bad explanations of the various interpretations of quantum mechanics. I won't go into detail here, but you can look at the slides later. And it's not, we shouldn't be worried that there are philosophical problems sort of with the explanations of quantum mechanics, because there have been for essentially every physical theory, including the examples I've given here of Newton's theory of gravitation and sort of understanding of heat and temperature. So it's not fundamentally different from that. So our CRQCs, so that's cryptographically relevant quantum computers that could actually break stuff that we're using, are they feasible? Well, I don't know, I'm not a physicist, but my sort of opinion is the experiments that have been done suggest that you can put even very big systems in superposition. So you may know about the Schrödinger's cat, the thought experiment. And you could think of that experiment as saying that very big things can't be put in superposition. But that might very well be true for something the size of a cat, but it's not true for the sapphire crystal, which is 16 micrograms. And if you think about how many atoms are in 16 micrograms, it's a lot. So yeah, we can probably build quantum systems and put them into superposition as we need to do for quantum algorithms. And we can make them big enough to solve cryptographic problems, I think. Okay. And so this is a report. It's in English, even though it's the German government department. And it's calculated basically how many qubits, how many gates, and so on you would need to break. These are elliptic curve discrete logarithms over this size of field. So the point here is not the particular numbers but that we have sort of fairly precise estimates of how big a quantum computer would have to be in order to do this. So what are the estimates for when they'll be available, if they're available? So BSI, that same German government institution that I was talking about, believes before 2040. So that is not very useful if we want an estimate that is pessimistic from the point of view of cryptography. Dan Bernstein is a sort of very famous and outspoken cryptographer who has estimated 2029 for well-funded private attacks. And that's not attacks that would break most deployed systems. It's basically showing that cryptographically relevant quantum computers are feasible and could scale up in principle. So if this estimate is right, and it's 2032 or something like that for a public demo of that, then we really need to get our skates on. So that's only 7 years. Okay, so how does Zcash depend on potentially vulnerable cryptography? It depends on it quite a lot. So we use signatures, we use encryption, and we use proofs, basically. And all of the properties are dependent on those. So this is if, so there's a caveat here, which I'll go into later, which depends on whether the addresses are public or available to an attacker. So there's this thing called harvest now, decrypt later attacks, and they're why we need to be worried about quantum attacks even before we have or we've seen a feasible working quantum computer, because an attacker can just collect ciphertext, collect public keys, and then when they have a quantum computer, they can break those ciphertexts. And the conventional wisdom is that this means that you should focus on fixing encryption. But if this is can happen in as short a time scale as Bernstein estimates, then we probably want to be thinking about other fixing other properties as well. It's not sufficient just to focus on encryption. And we know that the lead time for deploying protocols is really long. The lead time for analyzing new algorithms is long. And also, we don't just need systems to be secure. We need people to have confidence in them. And if it seems likely that quantum computing is going to be feasible, then that's enough to shake people's confidence, regardless of whether of how soon it actually works. Okay, so deploying new cryptography is difficult, though, and we might end up making things worse. We might introduce an algorithm that is broken. Okay, so let's look at some of the detail. In Zcash, we need to transfer notes to the recipients secretly. We currently do that by broadcast encryption, so just putting the ciphertext on the chain, having recipients trial decrypt them. And so that only works if the ciphertext doesn't reveal any information about which key it was encrypted to. So it happens that MLChem, which is an algorithm encryption algorithm that's recently been standardized by NIST, that has been proven to be key private. So that's nice. And yeah, there's a difficulty with that, which I'll go into later. So the other issue we need to consider is whether we might be introducing vulnerability if we move to quantum algorithms. So something that focused minds on this is that Zc, which is a isogeny-based encryption scheme, is now completely broken. And so that was representative of a whole class of algorithms that are now looking shaky. There's still some of them that might be secure. Monkey 3 had a soundness bug. That's a post-quantum proof system. Rainbow signatures were broken completely. So part of the problem here is that these post-quantum schemes, because they're having to defend against sort of attacks that previous schemes weren't, they're more complicated. And they can have side channel attacks as well as direct attacks. So what we could do is combine the post-quantum algorithms and pre-quantum ones that we already have some confidence in. So an example of this is X-Wing. If you're deploying post-quantum encryption, then I thoroughly recommend X-Wing. It happens that there are some issues with using it for Zcash. So it has pretty good properties. It's the public key size is just the sum of the individual algorithms, same for the ciphertext. But there's this issue with key privacy. So if both of the component algorithms are key private, then X-Wing is key private. I'm just asserting that, it needs proving. But there's a problem here, which is that if only one of them is key private, then the resulting hybrid scheme will not be key private. So let's say scheme A, that leaks the public key from the ciphertext, but scheme B is completely key private, then the hybrid will also leak A's public key. And so that's sufficient to say that it's broken for key privacy. And so when the proof that we referenced for key privacy of MLChem, it assumed hardness of this. This is module learning with errors. It's the sort of underlying problem that this lattice-based scheme depends on. And so part of the reason we're using a combiner is that we don't want to rely on that. I think there is a way around this, but it basically means that we can't use Xwing, and we can't use the analysis that's already been done on Xwing. The other issue here is that we currently have something called diversified addresses, which is really important for the combination of performance and privacy. So the idea is you can give out different diversified addresses to different counterparties, but when you try to decrypt, you only need to do it with one key. And the parties can't tell that they've been given variants of the same address. So how do we extend this to MLChem? Well, it's not obvious how to do it at all, because it depends on elliptic being approved. I think there's a way to do it, and I've explained how to do it here, but I'm not going to have time in this talk to explain how that works. But I think there is a solution. We need to sort of prove that that's secure, because there are a lot of subtleties that can make these schemes insecure. So how about proving systems? Let's say we've done encryption. So part of the issue here is that post-quantum proving systems require fairly large proofs. The scheme, I think it's Plunky 2 that requires 50 kilobyte proofs. I'm not sure whether Plunky 3 reduced that slightly. But either way, so it's unrealistic to have a 50 kilobyte proof per transaction. So that would significantly impact scalability. And we're less sure about the security of these schemes. I mentioned that Plunky 3 had a soundness issue. So we could try and use recursive proofs, so that so you do have a proof per transaction, but then so you prove something about some group of transactions, and then use a single proof to show that you've done that. So that's what recursion is. So we could use that for the size problem, and then use a proof combiner as for the confidence problem. But there's a problem with that as well, which is that we basically don't know how to do combiners for recursive proving systems efficiently. So yeah, that's an issue. And it's particularly an issue because we might need to deploy this relatively soon. So we can't just wait for a proof system and not do anything before then. So here's what I suggest. We deploy recursion using Halo 2, which is not post-quantum. And that gives us some scalability improvement. And then when we have a recursive post-quantum scheme that is both efficient, that has practical proof sizes, and we're confident it's secure, we switch to using that. But we've already done a lot of the engineering involved with deploying recursion. So the changes to the protocol, so apart from the proof system itself, will already have been done. Okay, and there are potential candidates for this second scheme, but it's a really, really fast-moving field. Okay, so we do know how to do proof system combiners, but as I said, the problem is recursion. Okay, signature combiners. So Zcash uses signatures for spend authentication, and so there's a non-essential use of them for balance checking non-malleability that we could get rid of. Okay, so we just basically include both signatures. That's one way of doing it, and that works. But it turns out that we might not actually need signatures. So we, as I said, we use them for spend authorization and binding, and that's to ensure balance. But we can just use a zero-knowledge proof for that. In a sense, zero-knowledge proofs are a generalization of signatures. And so, they're more powerful than signatures in some way. And we can just replace the signatures with proofs. Now, the difficulty with that is that we use signatures for sender authorization for a reason, and that's what has made the Keystone hardware wallet support practical, because Keystone only has to do signatures, it doesn't have to do proofs. So how can we sort of retain that advantage if we're replacing the signatures with proofs? Well, it turns out we only need a very small circuit that executes on that is proven on the hardware wallet, and is literally just one commitment, and so whatever is necessary to compute the public key from the private key, which could just be a hash function. So that is a very small circuit. There is still some question about whether it will fit in a hardware wallet, but I think probably for something like Keystone, or maybe even some of the more recent treasures, I don't know about Ledger, it would probably be practical. Yeah. And what we've effectively done here is construct a randomized signature scheme anyway, just from a proof system. So yeah, I just put this together quickly based on Sean's talk from yesterday, which I really liked, about the scalability of nullifier checking, and I think you can combine that scheme with everything I'm talking about here, but the scheme itself is not post-quantum because it uses elliptic curve scale multiplication. So an open question there about how we can make it post-quantum. Right. So size of addresses. This is one of the issues with switching to post-quantum encryption. Let's see, how am I doing for time? Okay, so you can see that MLChem public keys are about 10 times, or even the combination of transparent sapling and orchard keys. So yeah, that might be a problem. I'll show you what that looks like. Yeah, transparent plus sapling plus orchard. Originally, for the design of sapling, I was trying to get this online. Maybe I shouldn't have tried so hard to do that. And this is the same thing with orchard plus something post-quantum. Yeah, so that might not be practical. It's even worse when you look at it as a QR code. Okay. Yeah, this is some technical detail about whether we could actually compress the MLChem public key a little bit. I think it's not worth it because it would only be sort of a less than 20%. Okay, we could consider using other chems. As I said, site was broken. And most of these, if you look carefully, they're no improvement on MLChem, so there's really no point in even considering them because MLChem is standardized. The only exception to that is CSIC. And so this is potentially controversial because it said that isogeny-based encryption, some of these schemes have been broken. But CSIC in particular hasn't been broken. And I was talking to an expert on cryptography at a previous Hacks conference. Was it Real World Crypto? And he seemed to think that it was potentially secure still, but we'll see. Oh, and it's a little bit slow. So what can we do to mitigate this problem? We could transfer notes over a point-to-point connection. This has been discussed in previous sessions. So there are other advantages of using point-to-point communication, especially in terms of chain bandwidth. So it's probably worth considering anyway. But I think we would need MixNet because, as was also mentioned, things like Tor don't provide privacy against a global adversary. So NIM, there has been some work on using NIM with Zcash, and I think that's the approach to take there. But there are use cases that it doesn't support, like posting donation addresses on social media. The other thing that we could do is we could sort of use the blockchain to register addresses, and then you refer to those addresses. That also has difficulties because you need to send the transaction registering the address anonymously. So it doesn't really solve the problem of needing a separate anonymous communication mechanism. Okay. Oh, also you would have to, so if you want to use diversified addresses, you have to put each diversified version of them on the chain, and there might be sort of metadata timing correlations between those. Okay. So there's another thing that we can do, which was that the original Zerocash protocol was designed to have this property called everlasting anonymity. I think it's a bad name, actually. But the gist is that we still have the same privacy properties, excluding diversified addresses, in a post-quantum situation, provided that addresses are kept secret. And we maintain this property sort of throughout the development of Zcash. We made sure that all of the symmetric cryptography is using key sizes and sort of other crypto values that are large enough. And I don't need to go into detail here about Grover's algorithm, but it basically the conclusion is that it's much more difficult to build computers that run Grover's algorithm, which is what you would use to attack symmetric cryptography, than it is to attack public key cryptography. So I'm not particularly worried about any of the symmetric crypto in Zcash being vulnerable to quantum computers. So how do we take advantage of this property? So some protocols that are used in messages. So if you're trying to send your address to a counterparty, if you do it over one of these apps that have upgraded their protocol to specifically to address host-side cryptolator attacks, then that's probably sufficient, at least for now. And I think they will sort of move to fully post-quantum protocols at some point. So those are Signal and Apple iMessage, and basically nothing else. Not even, as I'll go into in a couple of slides, other apps that use Signal protocol can't really be relied on. But that only works if you tell your counterparties to keep the addresses private. And wallets at the moment are not really designed to keep addresses private. So it may be kind of slightly unrealistic to depend on this property of the protocol, even though I think it's an important property. Your wallet backups will contain copies of your addresses. So if the encryption that those backups are using, if they're either unencrypted or they're encrypted with an algorithm that is going to be broken by a quantum computer, then you don't have private addresses. And reply addresses can sort of weaken this property. So basically giving your counterparty your address, and if the counterparty is an adversary, then you give them your address. Okay. I think that's a duplicate slide. So no other messaging apps to pay attention to this property at all. A lot of messaging is not end-to-end encrypted at all. These systems, some of them claim end-to-end encryption, and they don't reliably have it at all. Here are a bunch of protocols that sort of rolled their own crypto, and none of it is resistant to house-side cryptolator attacks. As I said, even the ones that are based on Signal protocol. And the session here, they previously used Signal and then they were moved to something worse for some reason. Facebook and WhatsApp do use Signal, but I can't find any information about when or whether they're deploying the HNDL resistant ones, and I wouldn't trust them anyway because they have terrible policies. Okay, so what's next? So Sean and I will try and find out whether that idea for scalable nullifiers can work in a post-quantum setting. There was the idea I had about how to make diversified addresses work with post-quantum key privacy. And this is an important question. How should we decide how to prioritize post-quantum stuff? Okay, so let's leave it. Actually, I will go through the calls to action. Yes, if you're an ecosystem dev, do all of this, but I think the most important one is to treat addresses as secrets and pay attention to the security of wallet files. It's not okay to assume that they're less in need for security because they only have addresses and not private keys. Cryptographers learn about the constraints of real-world protocols. public key sizes and ciphertext sizes are a big deal. And I will see you in Sophia. And yeah, we need to take post-quantum security seriously. And in the meantime, we need to fight fascism, because otherwise all of the cryptography in the world is not going to help us. Okay, I'll answer some questions. So how much work is it in theory to implement any sort of quantum upgrades in Zcash? Years or months? Designing the cryptography is not years, but deploying it might be. In your opinion, what are you most concerned about as PQ crypto evolves moving into the next 5 years? I'm concerned about the possibility that everything may happen a lot faster than we think it might be. Because there was what seems to be a little bit of a breakthrough by Google, I think it was, in post-quantum error correction. In quantum error correction. And if that pans out, then we could see cryptographically relevant quantum computers faster than was previously thought, although it's still consistent with Bernstein's estimates. And then, yeah, I'm worried that the time to deploy major upgrades is very long at the moment, and we need to shorten it. Okay, I think that's everything. Do we have any more questions? The need to keep addresses private suggests that address rotation should be a high priority for all wallets. I completely agree. Fortunately, we're working on address rotation as we speak for Zashi. Outbound communications is a common topic. Has there been any consideration of rolling that in-house? I think this question was answered in a previous session, and I agree with the answer given there, which was that I think it was who said that so we should try and use stuff that has already been developed and already has a community around it, partly because that, this is my observation, that also increases the anonymity set. Anything else? I wrote a demo to encode an orchard address with X-Wing with Emerald Palace. It is actually a random address, but it's the right length. It's using the Python test vector encoding in Zcash test vectors. So I will publish the code. Yes. Anything else? Okay. I think that's everything. That was fun. See you all.